All right, so it's my pleasure to introduce you to Christoph Thäle from Ruhr University at Bochum. We met like 3 or 4 years ago, and we started working together, and it's my pleasure to invite him to our seminar today, where he'll talk about random cones. So whenever you want.
Thank you, David, for the introduction. I'm happy to give this presentation. Oops, want to go back. Yeah. I'm happy to give this presentation about the stochastic geometry topic. And this is about random will be, oops, what is going on here? Do you still see the screen?
Yeah, we see it.
Okay, I got some message on my tablet, so I don't know. So it will be about random cones, and it's based on several joint works with Zakhar Kabluchko from University of Münster, Sasha Marinic, Daniel Temesvari, and Dmitry Zaporozhets. So the object that we are interested in is easily defined. So it's going as follows. We are sitting on the d-dimensional unit sphere, and I denote this by SD. And on the d-dimensional unit sphere, we put n uniformly distributed random points. Okay. And to each of the points, u1 up to un, you associate the orthogonal hyperplanes, u1 perp until un perp. They partition the ambient space, which is Rd plus 1, in which SD is sitting. So this is Rd plus 1. They partition the space into random cones. And the picture is like this. So here you see the d-dimensional unit sphere. I don't know why I lose the connection always. So here you see the d-dimensional unit sphere. And I didn't put the points here, but I just put the hyperplanes. They dissect the space into cones, and regardless the distribution of the random points, almost surely you will see this number of cones. And this number is denoted by CND plus 1. So it's the number of chambers that you see in RD plus 1. If you start with n random hyperplanes, it's 2 times sum from 0 to d of the binomial coefficients n minus 1m. And this is a very classical result in dimension 2. This has been proved in the 19th century by Steiner and a little bit later by Schläfli in any dimension. So these are random polyhedral cones, and the object we are interested in is the following thing. So you see all these random cones. This is a finite number of random cones, and you can select one of them uniformly at random. And this random cone is called the Schlafly random cone. You have this finite collection of cones, and you select one uniformly at random. Let's say this cone here. And this is the Schläfli cone, which we denote by Sn. So we suppress the dependence on the dimension and just write Sn. This is a uniformly distributed random cone if you start with n uniformly distributed random points on the sphere. This is our object that we want to study, this random cone. And there's a very classical paper by Zakhar and Efron from the 1960s, where they computed the number of faces of this cone, or equivalently, the expected number of k-dimensional faces of the spherical random polytope generated by this Schläfli cone. So this is this polytope that you see on the sphere. It's the spherical polytope, and they computed explicitly the expected number of k-dimensional faces of the spherical polytope, or equivalently of this cone. And this is this number here. So you see something, and then you see the C numbers. These are the numbers that we have defined here. And you can also, and they also did the analysis when n goes to infinity, k is fixed, d is fixed. Then they proved that this converges, this fancy number here converges to 2 to the power d minus k times d choose k. And if you are familiar with the number of k-dimensional faces of a cube, you will recognize this is exactly the number of k-dimensional faces of the cube. And they closed the paper by the sentence that, loosely speaking, the expected cross-section of the Schläfli random cone Sn is a cube. And well, obviously, this is true if you look at the number of k-dimensional faces, but our question was, is the same also true if you look at the shape of the cone, or the shape of the cross-section of the cone? And
sorry,
well,
Christoph, one question. The convergence is when n tends to infinity, when the number
yes,
of
convergence
points.
and n tends to infinity.
And k is fixed.
Yeah, kd are fixed and tends to infinity. Then just this ratio here converges to yeah. Then you just see this binomial coefficient coming from, yeah. You have to see which one of those is winning and how this is going. Yeah, this is very easy here. But as n tends to infinity, in all what I tell you, the dimension is fixed. Although you can also do the high dimensional analysis when d tends to infinity, but this will be not our topic for today. Yeah, as I said, we want to see whether really also the sentence here is true if you look at the shape of the cross section of the cone. But the combinatorics is fine, but the shape. And first of all, well, you have to make sense of what is the shape of a cone, or how can you describe the shape of a cone. And we do this by means of the so-called profile of the cone. How do we do this? Well, here's the Schläfli random cone. And it cuts out from the sphere a spherical polytope. And in this spherical polytope, you pick a uniformly distributed random point. This is the white point that you see here. And at this point, you look at the tangent space. And now you intersect the cone with this random tangent space. And this is what we call the profile of this Schläfli cone. So formally, you have this spherical polytope, Sn intersected with the sphere. This is the spherical polytope. You pick this uniform random point, that's the white point, and then you intersect the random cone with this random tangent space. And this is this red thing here, and this is what we call the profile of this cone. And this, in a sense, you can say describes the shape of the cone. And if the statement of Zakhar and Efron is correct, then this profile should converge in a suitable sense to the cube, right? Because this is just a random polytope in Rd. If you identify this tangent space with Rd, then this is a random polytope in Rd, and this should somehow converge to the cube, at least if the statement of Zakhar and Efron is correct. But unfortunately, or fortunately for us, the statement is not correct, and the things are much more interesting. And here's the result that we proved with Zakhar, Kabluchko, and Daniel Temesvari in, well, it was probably 2018, and we hope that the paper will appear this year. Okay, so you look at these profiles as n goes to infinity. Dimension of the sphere or the cones is fixed. These profiles are random polytopes in Rd. And well, the cones, they get smaller and smaller. So these random polytopes get smaller and smaller as well. And so if you want to have a meaningful limit, you have to rescale. And the right scaling is here, blow up everything by factor n. And what we prove is that these profiles, they weakly converge, but they don't weakly converge to the cube. It's more interesting, they converge to the typical cell of a stationary and isotropic Poisson hyperplane tessellation in Rd with a certain intensity, which is just a scaling factor. So this shouldn't bother us. So, and what I want to do is, well, first of all, we have to make sense of what does weak convergence mean here. This is the convergence which takes place in the space of compact convex subsets supplied with Hausdorff distance, and the related weak convergence of the random objects here. And so you know how, what in which sense convergence takes place, but of course, maybe you don't know what this limiting object is. And this is the next thing I would like to do with you, to introduce you the object to which it converges, and this has to do with this picture here. And then I would like to explain to you how to deduce this result, because this is interesting. Namely, we were not able to deduce this from any of the existing tools that we had for weak convergence of random polytopes. And what we had to do is to develop a new criterion for weak convergence of random polytopes, which is based on the topological structure on a certain subspace of polytopes, which might be of interest independently of this result and might be applicable in other contexts as well. But first of all, I would like to explain to you what this picture here means and what this limiting object is, the typical cell of the stationary and isotropic Poisson hyperplane tessellation. So what is it? So everything takes place in RD because we are now in this tangent space in which these profiles are supposed to converge. And this space of hyperplanes in RD, which we identify with this tangent space, this carries a very natural invariant measure. And this measure can be described as follows. So if you have a set of hyperplanes A, the measure assigned to this set of hyperplanes should look as follows. So you parameterize hyperplanes by unit normal vector and distance to the origin. So unit normal vector is P here. This is a point on the sphere. Now D minus one-dimensional sphere because it's the sphere in the tangent space. And T is the distance of the hyperplane to the origin. So this is this very natural measure because you have here the spherical Lebesgue measure or normalized spherical Lebesgue measure. It's up to you what you do. It only affects constants at the end, which are not of interest for us. And so this describes the direction of the hyperplane. So they are uniform. And then the distance is uniform in the sense that you have the Lebesgue measure here. This is the invariant measure of hyperplanes. So invariance means here it's invariant under translations and rotations. So the natural action of the group of rigid motions on the space of hyperplanes. Well, and if you have a space and the measure, then you have Poisson processes that you can define. And well, that's exactly what we do. So what we mean by a stationary and isotropic Poisson hyperplane process is just a Poisson point process on the space of hyperplanes. And the intensity measure is just, if you want, a constant multiple of this invariant measure mu. And if you visualize this Poisson hyperplane process, then it looks like this here. So you have infinitely many hyperplanes now distributed all over your space in a sense in a uniform way, because if you look at these hyperplanes through a spherical window like here, then regardless where your window is sitting in space, the distribution of this picture doesn't change. It always looks like this. And these random hyperplanes, they obviously dissect the space into random polytopes, right? These are the random polytopes. These are the cells of this hyperplane tessellation. These are random polytopes, countably many. And one of them is of particular importance. This is the typical cell. And how do we define the typical cell? Well, first of all, we supply each of these random polytopes, each of these cells, with a center. Just a reference point, and you are pretty much free to choose one of these reference points, but for us it's very convenient to choose inside these random polytopes a uniform, in each of these polytopes, a uniform random point. A uniform random point. So this could be the blue point here. And then I just lost connection again. Here I'm back. And now you do the following thing. You look at the window of size of volume 1. Let's say you look at the unit cube or a circle or a disk, a ball of volume 1, and you take all these centers and the corresponding polytopes around them, and you shift them to the origin. Yeah, you shift all these polytopes to such that their center is now at the origin. And you do this with all the centers that you see in your volume 1 set. Let's say the unit cube or the ball with radius 1. This gives you a probability, this gives you a measure on the space of polytopes, and you can normalize it to be a probability measure. And now if you sample a random polytope according to this measure, this polytope will be called the typical cell. And intuitively, you can understand this as follows. You take a super large window, maybe the one here, and then you see only with probability 1 finitely many of these random polytopes, and you choose one uniformly at random from them, regardless of size and shape, and shift it to the origin. And now you expand your window and expand, and then the limit of these distributions of these random polytopes that you always shift to the origin, this will be your typical cell. So this is, you select uniformly at random from your infinite collection of random polytopes 1. Of course, this is not possible because you have infinitely many, but if you do it like this here, then this is the notion of the typical cell. And exactly this is the limiting object. So the limiting object that we see as the profiles of these cones is this Poisson hyperplane process typical cell. So you need this infinitely many hyperplanes. You select one of these random polytopes uniformly at random. This is the typical cell. So now you know how the convergence takes place, and probably the statement makes sense to you because you know the limiting object. How do we prove this convergence? For this, we need a few notation. We need the space of compact convex subsets supplied with usual Hausdorff topology. This is the space in which we want to show weak convergence. This is the space calligraphic V. Then we have the space of polytopes sitting inside this space of compact convex subsets. This is a subspace. And then we need a further subspace, PDM. This is the subspace of all polytopes having exactly m vertices, such that all first coordinates of these vertices are different. This is this space here. And this space has a nice representation space in Euclidean space. This is the key for us. Representation spaces in Euclidean space will be always denoted by this tilde here. And this, you can identify the space of polytopes with the space of vertices of these polytopes, namely, you take m tuples of points in Rd, right? Points in Rd such that the first coordinates are all different, and let's say they are ordered increasingly. And these points are supposed to be in convex position. These are the vertices of these polytopes. You represent all the polytopes in this space by their vertices. And in this representation space, of course, this is a subspace of Euclidean space. You have the Euclidean topology, which is hopefully more easy to work. And now we have this space nicely identified with a subspace of a Euclidean space or a subset of Euclidean space. Now you want also a representation space for the space of polytopes. Well, not all polytopes, but polytopes whose first coordinates are all different. The first coordinates of the vertices are all different. Well, you just take the disjoint union of these representation spaces, and you supply this with the disjoint union topology. And well, this is induced, this is the disjoint union topology induced by the Euclidean topology in each of these factors. Again, this is a Polish space. And well, with what can this be identified? Well, with the union of all these spaces here. So this is now a subset of the space of compact subsets. So these are these polytopes here. This is PD infinity and PD infinity tilde. So this is the correspondence. You have a correspondence within these two spaces as you have a correspondence between these two spaces. So here's a little diagram. Use the space of convex subsets for which you want to show a weak convergence. In this space, the space of polytopes is sitting. In this space, this PD infinity is sitting. So this union space is sitting. And also you have this space of polytopes with exactly m vertices sitting down here. And for each of these here, I don't know, do you see my pointer?
Yeah, it's stuck. Oh no, it's okay now.
It got stuck somehow. I don't know. Can you see my mouse?
Yeah, the mouse, yes.
Maybe not. The mouse, yes. And then I do it with the mouse. Maybe it's, I don't know why it doesn't work. But okay, if you see
Yeah,
my
okay.
mouse, it's fine as well. Yep. Okay. So you have this space of polytopes here, space of PD infinity. This is this special space of polytopes, and sitting inside the space of polytopes with M vertices. And here on the left-hand side, you have the representation spaces for these two subspaces of polytopes. Identification is easy. You just identify an M tuple with its convex hull. That's how you go from left to right. Right, and if you want to do it in the big space above here, then you have to glue together these mappings. Okay, and the first observation is, well, if you want to show weak convergence in the space of compact convex subset, as we would like to do, it's sufficient to prove weak convergence in this representation space. Why? Well, this is just the continuous mapping theorem. Right, it's just the observation that all these mappings iota I they are continuous, and the rest is, well, you just follow these arrows, and that's nice because hopefully to show weak convergence in this representation space is easier because, yeah, well, this is just a disjoint union of subsets of Euclidean space, and hopefully Euclidean space are easier to handle. But the next question is, of course, well, is this of any practical interest? How can we prove weak convergence in this representation space PD infinity tilde? Well, as a reminder, here is this representation space P infinity. This is just a disjoint union of all these representation spaces PDM, so of polytopes with M vertices. And now on each of these factors, of course, you have a Lebesgue measure sitting, where it's just Euclidean space, and you can glue all these Lebesgue measures together, or you can be more general, you can say you can take on this space PD infinity tilde a measure, mu infinity D, such that the restriction to any factor is the Lebesgue measure on RD. You can, for example, just glue together Euclidean Lebesgue measures. And then we have the following Schläfli type lemma for random polytopes. So suppose that you have a sequence of random polytopes in RD, and you have another random polytope T also in RD, such that with probability 1, all your random polytopes and the limiting random polytopes are sitting in this space of polytopes PD infinity. So all vertices have different coordinates. This is strictly the case for us. And then now it comes. Now assume that if you identify your polytope with the representation, with the vertex representation, then you suppose that this identification has a density with respect to this infinite Lebesgue measure. And we also suppose that the limiting object has a density. This is the density phi, and for the random polytope Tn, this is the density phi n. And now suppose that you have pointwise convergence of these densities. This is now everything is in Euclidean space here. Then you have weak convergence in the space of compact convex subsets with respect to the Hausdorff distance. Maybe you want to see the simple argument. So first of all, if you want to prove weak convergence in KD with respect to Hausdorff distance, we already saw that this is it's sufficient for this to prove weak convergence in this representation space. So the only thing that we need to prove that is once you have convergence of these densities in the vertex representation space, you have weak convergence in the space PD infinity. So just take a bounded continuous function on that space. And then it's very easy. I mean, you have to show that integrals of bounded continuous functions converge, so that the difference converges to 0. But these measures here, these are the vertex representations of the distributions of these random polytopes. They have densities. Just plug in that they have densities with respect to this infinite Lebesgue measure. Now use that h, the function h, is bounded. So you can take out the infinity norm of h and use, well, triangle inequality. And then you have to estimate, or you have to say something about the difference of these densities. Well, but this is our assumption, the densities converge. And then this is the classical Schläfli lemma, that if the densities converge pointwise, then you have weak convergence. And which means that these integrals go to 0. So this must go to 0. So this is now a criterion for weak convergence of polytopes, which plays with these vertex representations. So you need somehow to have access to the densities of these vertex representations. And yeah, question is, how can we work with this? And the work makes a little detour around, and it goes via two other models of random cones and polytopes. So recall that we are interested in the random Schläfli cone. So this is the polyhedral cone selected uniformly at random from the collection of all cones. So here you have all these cones, and we have selected uniformly at random one of them. This is the Schläfli cone. There's another object which is hidden here in this picture. This is, let's say, the cone which contains a fixed point. And as a fixed point, since everything is isotropic, you can choose whatever you want. Let's say you choose the point as a point, the south pole. This is the red point here, the south pole of the sphere. And with probability 1, this south pole is contained in one of the cones. And this is the cone Sn minus E. This is the cone which contains the south pole. It's the green cone here. Next, we did another model. Now we are not in the sphere, but only on a half sphere. This is SE for me. So this is just a half sphere. And on the half sphere, you distribute randomly, uniformly distributed random points, x1 to xn. And you just take the cone spanned by these points. This is just a positive hull of x1 up to xn. This is the cone Rm. This is the green cone here, the light green cone. And to this cone, you can also associate its dual. That's the dual cone. So this is the set of all points in Rd minus 1, such that the scalar product between each point of the cone Rn and y is less than 0. So you have just the right angle between these two bounding lines here. So the polar cone is this red cone here. And between all these cones, the blue, the dark green, the light green, and the red cone, there are relations. And the relations are as follows. And these relations follow by rather straightforward computations. I don't want to show you, but you can check that these are true. So first of all, the polar of this half sphere cone Rn, so the red cone, has the same distribution as the south pole cone here. So these are identically distributed as random cones. So the two cones that look downwards here, they are identically distributed. This is observation number 1. Observation number 2, the south pole cone here on the left is the size-biased version of our Schläfli cone. What does it mean, the size-biased version? Formally, it means the following thing. The following identity is satisfied. What is the size here? How to measure the size of a cone? Well, the size is just a solid angle. It's the opening angle of this cone, formally defined as follows. So if you have a cone C, you take a normally distributed random variable n in the linear hull of this cone and ask for the probability that it's contained in the cone. This precisely describes the opening angle of this cone. And this is the size. And what does size biased mean here? Well, you have this random collection of cones here. And the Schläfli cone is one selected uniformly at random from these cones, from this collection of cones. This means that you select a cone uniformly at random regardless of size and shape. But there is also another possibility. You can assign to each of these cones the opening angle and then select a cone according to this opening angle, meaning that angles with cones with a small angle have a smaller chance to be chosen than cones with a larger angle. So you select according to this opening angle or proportional to this opening angle. This means you size bias. And if you size bias the Schläfli cone, exactly the south pole cone comes out. These are the two boxes here. So there's a relationship between these four cones: the red cone, the light green, the dark green, and the blue cone that we are interested in. And the question is, why does this help? It helps because we know something about the red cone. The red cones are the cones that are easy to handle, in a sense, easy to handle. And how is the result? The result we can prove about the red cones, these are the polars of these half-sphere cones, is as follows. So you have the lower half-sphere, and here's the south pole. You take the tangent space at the south pole. No, sorry, it's not the red, it's the green one, it's the R. So you have here the north pole of the sphere. You look at the tangent space at the north pole. You intersect it with the cone. And well, this gives you a random polytope in this tangent space, which you identify now with RD. So this IE is just an isometry identifying the tangent space with RD and the point E, the north pole, with the origin of RD. So since the cones are N, they are opening up, these random polytopes get larger and larger. So to have a meaningful limit, you have to rescale with something, and the something is n to the -1. So you have to make them, you have to push them back again. And if you look at the sequence of these random polytopes in RD, they converge to the convex hull of a Poisson point process in RD minus the origin, which has the following density function. It's a constant times 1 over norm to the d+1. So this gives you an infinite collection of random points. This is this Poisson point process. And if you take the convex hull of them, this will be a polytope. And this weak convergence here, it's a random polytope, and this weak convergence will take place in the space of compact convex subsets with respect to the Hausdorff distance. So how do these polytopes look like? So here are simulations in the plane and in dimension 3. So these black points here, these are the points of this Poisson point process. Somewhere where my mouse is, there is the origin. And around the origin, oops, sorry, I have to go back. Around the origin, you will see infinitely many points because this density function is not integrable at the origin. You will see in any ball around the origin, infinitely many points. But outside of any ball of positive radius, there will be only finitely many points because this the integral of this density here around each ball of positive radius converges to a constant. So there must be only finitely many points outside here. So if you take the convex hull of them, this will be with probability 1 a polytope. And this is exactly the limiting object that comes out here. And here you see a simulation in R3. Somewhere sitting inside this point cloud here is the origin of R3. And again, you see around each ball infinitely many points, but outside only finitely many points because this density becomes integrable. And if you take the convex hull of these finitely many points, this will be a random polytope, the convex hull of this Poisson point process. And this is exactly what you see at the limit. And now with the help of this result and the two blue boxes that we have seen, we can now at least morally complete the proof. Why is now the result for the random Schläfli cone at least why does it make sense? Well, let's recall, we have a connection between all these cones. So we have a result for the cone R, but we are interested in the cone, in the dual of this cone. So we have to look at the dual also of this limiting object. It's the dual of this Poisson point process. So since this is the dual of a convex polytope, so defined as a convex hull of random points, the dual must be the intersection of random half spaces. And what comes out is the zero cell of this stationary and isotropic Poisson hyperplane tessellation. What is the zero cell? Well, it's just the random polytope in the stationary and isotropic Poisson hyperplane tessellation containing the origin. That's why it's called a zero cell, because it contains the origin 0. This is the limiting object of these cones, of these polar cones Rn circ. And they have a relation to the South Pole cone, and the South Pole cone, they have a relation to the Schläfli cones that we are interested in, and the relation is by a size biasing. So if we want to go backwards, we have to size D-bias, and the size D-biased version of the zero cell is the typical cell. And that's why, at least morally, the result should be true. Details are complicated, but this is why the result should be true. So here's a diagram. Here's the cones we are interested in. If you size bias them, you go to the South Pole cones. They are equal in distribution to the polars, the duals of these half-sphere cones. So by polarity, you go to the half-sphere cones. For these half-sphere cones, you know the convergence from the paper with Zakhar, Sasha, and Daniel. Then you have this weak convergence. And then by polarity, you go back to the polar, which is the zero cell. Well, this is the zero cell. And by a size D biasing, you end up with the typical cell, which is exactly the implication that our main result says. So to walk around this diagram is not easy and requires a lot of effort. But since we have some time, that's very good. I can show to you how to prove this crucial weak convergence Rn converges to the convex hull of this Poisson point process, because this is the part where here where our Scheffé type lemma for random polytopes comes in. And this is a nice application that hopefully convinces you that the lemma is not only an abstract device, but you can actually work with this. So let's recall what we need to prove. So we need to prove that if you take the positive hull of uniformly distributed points on a half sphere, this converges to something. Right. So this is the cone whose weak convergence we would like to study. And we would like to study it via the profiles, the intersections with the tangent space at the North Pole. So we intersect the cone with the tangent space at the North Pole. We make this identification of the tangent space with RD, and we need to rescale by n to the -1 in order to make this meaningful. And well, if you just compute the distribution of these points that you will see here, you will see the following density appearing. Namely, this is just the density that you get by if you do the gnomonic projection to the tangent space, and the points that appear here have the following density. So it's a constant, the normalization constant, and then you see here 1 minus 1 plus norm squared to the power d plus 1 over 2. And so this random polytope that we are interested in is just the rescaling of the convex hull of n IID points with exactly this density. Okay, and now what we have to do is to compute the density of the vertex representation of these random polytopes on that representation space. Okay, let's do it. Well, this representation space is the space of polytopes having exactly m vertices, all coordinates different. This doesn't hurt because this is an absolutely continuous density, so this will be automatically satisfied. So what we need to do is you have n points, the convex hull of n points here, and somehow you need to sort out these m vertices. So you have to choose from these n generating points the m vertices. This is the first factor that we have here. And then, of course, you can also permute. You have, this is this m factorial here. Then these points are chosen with respect to this density fd plus 1 over 2. But of course, there is a rescaling with n to the -1, which results in a factor n to the d here and a factor n here, because we are just in n-dimensional Euclidean space. And then there's a second factor, which takes into account all the other points which are not vertices. Well, if they are not vertices, they must sit inside the convex hull of the others, right? So, and what is the probability for this? Well, it's just the integral of the convex hull of the vertices that we have chosen here in the first factors of the density of these points. Again, this is fd plus 1 over 2. Then there is the factor n to the d and n here because we rescale by n to the minus 1 in our Euclidean space. And this is just a probability that the other points, or at least one of the other points, is sitting inside the convex hull of the others. And since they are IID, you just need to take them with to the power n to the power n minus m, because you have in total n points, and m are already gone because they form the vertices. And now you have to analyze this density here as n tends to infinity. Well, this is easy. First of all, you simplify binomial coefficients and this m factorial here. This gives you this. Well, then you plug in the density. Then a factor is coming out. This is this 2 to the omega d plus 1. By the way, omega d plus 1 is the surface area of the sphere. This comes to some power because this is an m-fold product. And then it's the product of these densities here. This is just plugging in the definition of the densities. Integrating with respect to the convex hull is the same as, well, it's a probability measure. So 1 minus integration of the complement of the convex hull. So you integrate the complement of the convex hull, again, just this density here. Next step. You just take out from this expression here all the n's, or most n's that you can. You take out from the brackets this n square. You take this out, but if you do this, the 1 becomes a 1 over n square. And a certain power of n appears here if you do the computations correctly. Here the same. You take out this n square from the brackets. This makes this 1, this transforms this 1 to a 1 over n square. And then you simplify with this power here and this n here, and it gives you a 1 over n. This is very nice because this first fraction here, this behaves like n to the m, which cancels nicely with this 1 over n to the m. 1 over n squared just goes to 0. And here, 1 over n just goes to 0. And you are left with 1 minus 1 over n times a certain constant to the power n minus a fixed number. This doesn't hurt. So what does this mean? Well, this converges too. Well, constant remains. The product of these terms remains, but only norm squared to some power. And the power is the 2's cancels out. Here it's the power d plus 1 here. And this goes to an exponential term, e to the minus this constant. So this is the limit of the densities of the vertex representations of these random polytopes. The only thing is we need to identify this limiting density with something. And this is done in the next slide. So the claim was that the random polytopes converge to the convex hull of the Poisson point process pi on Rd minus origin with this density function. Well, this already looks like the right thing, but let's compute the density of this convex hull. So the convex hull of this Poisson point process on this representation space of polytopes with m vertices. Again, you have to assume that all the vertices have different first coordinates, but with probability 1, this is satisfied anyway for our random polytopes because, well, this is just absolutely continuous. Well, what is the density? Well, you first need to pick the m vertices, and then you have to ensure that outside these points, there are no further points. Meaning that outside of the convex hull of the points that you claim are the vertices, there are no further vertices. There are no further points, meaning that the Poisson point process does not put any mass there. Okay? Then plug in, well, since this is a Poisson point process, this is exponential minus integral of the density over this region. And now you can plug in the definition of the densities. And this is this guy here, which you recognize, hopefully, because this is exactly the density that we have seen. So, which means that we have proved pointwise convergence of the densities on the space of vertex representations of these polytopes. And now our claim follows from the Schläfli lemma. So this is, I think, a really nice argument how to prove, or how to tackle a weak convergence of random polytopes. And in a sense, if you look at these profiles of the cone, also weak convergence of the random cones. So again, here's our result that I convinced you should be true. So if you look at the profiles, so these red polytopes here of the Schläfli cones, if you rescale them by factor n, they weakly converge to the typical cell of a stationary and isotropic Poisson hyperplane tessellation. And there was some constant hidden in our computations that I didn't specify. But if you do everything carefully, then you will find out the right constant. So let's come back to the paper of Zakhar and Efron. So they say, loosely speaking, the cross-section of the Schlafly random cones, they are cubes. Well, this is not entirely correct. This is not true. The cross-sections are not cubes. They are typical cells of stationary and isotropic Poisson hyperplane tessellations. But, I mean, there was a point in their statement, because what they said here is true if you look at the expected number of k-dimensional faces of these cross sections, where they showed that they converge to the number of k-dimensional faces of the cube. But how to explain this? Well, this is very easy, because it's for a long time well known that the expected number of k-dimensional faces of the typical cell is exactly, there is an expectation here which shouldn't be there, this is just the number of k-dimensional faces of the cube. This at the same time also explains the Zakhar and Efron result, because this is now immediate. That convergence of these cross sections on the space of compact convex subsets to this typical cell implies convergence also of the expected F vector, and in particular implies that the expected F vector of the cross section converges to the F vector of the cube. This is now a direct consequence. Okay, so this is all I wanted to tell you for today. If you want to know more, you can have a look at the few papers we wrote. So there's first of all the paper where we look at the random cones generated by random points on half spheres. This is one of the ingredients. To show the convergence, we need to develop this new weak convergence device I showed you, and we took care of all the details. This is the second paper here, and well, in the background of everything are densities of a so-called beta type, and the convex hulls of these densities are so-called beta polytopes. And also our results admit an interpretation in terms of beta polytopes and these Poisson polyhedra. These are the cells of this hyperplane tessellation. And if you are interested in the fundamentals of this theory, you can have a look at this article, the last one. And well, it just remains to thank you for your attention.
Well, thank you very much, Christoph, for this nice presentation on random cones. If anybody has any question, you can unmute yourself and ask directly the question. No questions?
No questions?
Okay, I have a question. Do your result give something about the asymptotics of the expected value of the faces of the random profile of the random polytope you get when you don't fix the dimension of the face, when it moves with the number of vertices, like let's say n-1 dimensional faces?
Yes. Yes, you can
sense?
say something, but this is another work. This is a recent work with Zakhar and Thomas Gottland. This is a PhD student of Zakhar, and where we exactly went into this direction. So we looked at the random Schläfli cones, their F vector and the vector of conic intrinsic volumes and conic Quermass integrals, where all the parameters can go to infinity. In particular, the dimension goes to infinity. And we prove for the expectation, we prove central limit and non-central limit type of results, large deviations and stuff like this. So the answer is yes. This has been done in this other paper. Yeah. So high-dimensional asymptotics can be analyzed. This is very interesting because it's this becomes very analytic because you have the formulas. For example, for the expected conic intrinsic volumes, and they form the probability measure on the integers 0 to d, these that I mentioned, and they satisfy central limit theorems, and you can analyze these probability measures, the induced probability measures, by means of modified convergence and Fourier analysis. And yeah, so we did that. And that's a quite recent paper with Thomas Gotland and Zakhar Kabluchko. Yes, if you want to have a look at this, you can check this paper.
Okay, thanks. Good to know. Anybody else? Are there any other questions? No, if not, then we thank you for this nice talk, and I'm going to stop recording.
Thank you very much.
Thank you.